is it possible for us to reduce ambiguity or eliminate ambiguity? Yes, there are some techniques for reducing ambiguity. No general purpose algorithms exist to test for ambiguity in a grammar or to remove it when it is found, but still we can reduce the ambiguity by getting rid of first epsilon production. If I have S tends to epsilon, then such type of productions are called as epsilon productions. They, if once eliminated, reduces the ambiguity. How? We will see an example. Next, the rules with symmetric right hand sides are leading to ambiguity. So, they also, if those rules are been eliminated, then also we go for reducing ambiguity. For example, S tends to SS, E tends to E plus E, such type of rules are symmetric. So, what we have to do is, the grammar is ambiguous if it is both left and right recursive. So, we have to eliminate either left one or right one. We will see an example for this. Then rule sets that lead to ambiguous attachments of optional postfixes also leads to ambiguity. Once eliminated, can reduce ambiguity. We can't say here it will completely overcome ambiguity, but to some extent we can reduce ambiguity by getting rid of these three. So, first we will take up with getting rid of epsilon productions, that is like S tends to epsilon. So, given a grammar V summation RS be a CFG, the following algorithm construct a G dash such that L of G dash is equals to L of G minus epsilon, that is G dash contains no epsilon rules, and the algorithm used is remove epsilon productions from the context free grammar given. So, initially what we do, all the rules written in G are considered in G dash, then find a set n of nullable variables in G dash, then repeat until G dash contains no modifiable rules that haven't been processed. What do you mean by modifiable rules? Given a rule P tends to alpha q beta, where q is nullable, if so, then what we do? We add the rule P tends to alpha beta if it is not already present in the rule set, and condition to add this P tends to alpha beta is if alpha beta is not equal to epsilon and if P is not equal to alpha beta. So, this condition will overcome introducing indirectly unit productions which are needed to be eliminated later. So, once we obtain the modifiable rules, we go for deleting all the rules which are of X tends to epsilon from the grammar, and after deleting the nullable variables or nullable productions, whatever grammar we have, that grammar is free from epsilon rules. Now, before going to eliminating epsilon rules, what actually you mean by nullable variables and modifiable rules? A variable X is nullable if and only if there is a rule X tends to epsilon. If I have X tends to epsilon a rule, then X is nullable. Or if there is a rule X tends to PQR and all these three PQ are also nullable, then X is nullable. So, compute n the set of nullable variables as follows. How? The set n to the set of variables that satisfy the first condition, then until the entire pass is made without adding anything to n, do what to be done? Evaluate all other variables with respect to 2. If any variable satisfies 2 and not in n, then insert it. So, this is how we go for identifying the nullable variables, and this is the rule for introducing the modifiable rules. So, quickly we will see an example wherein the grammar consists of S, T, A, B, C, A, B, C, terminal symbols are A, B, C, and the rule set is S tends to A, T, A, T tends to ABC, A tends to AC or C, B tends to BB or C, and C tends to C or epsilon. So, these are the rules. Start symbol is yes. Now, given this grammar, applying remove epsilon productions algorithm, we must eliminate epsilon productions from this particular grammar. So, directly from this grammar, which is epsilon production, C tends to epsilon. So, first step is what? We must identify all nullable variables. So, which all are nullable variables? According to the algorithm, first C tends to epsilon. C is nullable. Then, once C is nullable, if you see B tends to C and C is nullable, it means what? B is also nullable. Similarly, A tends to C and C tends to epsilon, it means A tends to epsilon. So, A is also nullable. So, from pass 1 of this algorithm, we came to know that A, B and C, all these three are nullable. Next, in the next pass, if you see A is nullable, B is nullable, C is also nullable, then ABC is nullable, then T tends to ABC means T is also nullable. So, by the second pass, the nullable variables are T, A, B and C. Can S be nullable? No. So, by the end of pass 3, there are no new elements added. So, the nullable variables are A, B, C and T. Hence, identifying the nullable variables algorithm stops here. So, once we are done with this, next what we are supposed to do? We must go for modifying the rules by applying the nullable productions or nullable variables. How? Now, as you know, this is the grammar and nullable variables are A, B, C and T. In the third step, new rules to be added. So, what is the first rule? S tends to ATA and T is nullable. Is T nullable? Yes. Then the new rule added is S tends to AA. Next, coming to T tends to ABC. Here all three are nullable. So, if I apply A as nullable, I will get BC as a new rule. If B is nullable, I will get AC as a new rule, and if C is nullable, and then I will get AB new rule. Then, among these three rules, if A is nullable, I will get B new rule added. If B is nullable, C new rule added, and if C is nullable, then A is a new rule added. So, for T tends to ABC, the new rules added are T tends to AB, BC, AC, A, B and C. Coming to A tends to AA, A is nullable. So, A tends to A is the new rule added. Similarly, B tends to BB. So, here B is nullable. So, B tends to B is the new rule added. Once we go for adding the new rule, next is what? The final grammar obtained excluding C tends to epsilon. The final grammar obtained after eliminating epsilon rules are S tends to this production as it is ATA, and new rules of S are AA. Next, T tends to ABC, T tends to ABC rule as it is, plus additional rules are AB, BC, AC, A, B and C. Coming to A tends to AAC as it is, new rule added is A. Next, B tends to BBC as it is, new rule added is B. Last, C tends to C. C tends to epsilon is been eliminated, and this is the grammar obtained which is free from epsilon productions. You can see here in this grammar, do you have epsilon production? Yes. Now, after applying this remove epsilon production, the grammar obtained is this grammar which is free from epsilon productions. But remember, this grammar is equivalent to and must be equivalent to this grammar. Hence, we have eliminated epsilon productions. Next question is, if you have seen the first foremost grammar written by us, that is language A raised to n, B raised to n, where n is greater than or equal to 0. What is the first string from that particular grammar? First string is epsilon, then AB, then AABB, and so on. What if the language itself includes epsilon as the first string? We have to retain it. At that time, what to do? Sometimes the language contains epsilon and it is important to retain it. Why it is important? Because that is also one string present in that particular language. At that time, along with eliminating EPS, we go for adding one more algorithm called as at most one EPS, wherein first we go for applying remove EPS and obtain the grammar. Once we get the grammar, we go for checking if SG is nullable. Is it nullable? Does epsilon belong to this particular language? If yes, then what? Create a new grammar wherein a new start symbol will be S star. Then add one more rule in the rule set. S star tends to epsilon. This is for epsilon string, and S star tends to the previous start symbol present in this particular grammar, and then return the grammar. Let us see one example for the same balancing the parenthesis. You can see here this was the grammar written S tends to SS, S tends to opening parenthesis, S closing parenthesis, S tends to epsilon. So, first let us apply remove EPS. So, on applying remove EPS, we are eliminating S tends to epsilon. So, S tends to SS as it is, S tends to opening parenthesis, S closing parenthesis as it is, and if I apply S as epsilon, I will get S tends to opening parenthesis and closing parenthesis, and S tends to epsilon is been eliminated. So, this is the grammar or the rules obtained after eliminating the epsilon productions. So, once we have eliminated epsilon productions, next what we do? We go for generating a new start symbol S star and include these two rules. So, S star tends to epsilon, first rule added, and one more is S star tends to S, which is the start symbol. The start symbol of this grammar is S. So, S star tends to S, where S is these three rules written as it is. So, this is the grammar obtained for after eliminating epsilon productions and including the first string as epsilon in this grammar. So, by applying remove EPS and at most one EPS, what we have done? We have eliminated epsilon productions. But will it be possible that this grammar is free from ambiguity? So, this is a grammar obtained. Now, if we go for putting the parse tree for the same string what we had done before and proved that the grammar is ambiguous, you can see here we have only one parse tree. S star tends to S, S tends to SS, S tends to S opening parenthesis, S closing parenthesis, again S tends to opening parenthesis, S closing parenthesis, S tends to epsilon, and again S tends to opening parenthesis, closing parenthesis, opening, opening, closing, closing, opening, closing. So, if you try to put one more parse tree also, it is not possible for you to obtain two different parse trees. Hence, this grammar is ambiguous. Can I say? Okay. Check for this string opening, closing, opening, closing, opening, closing. Same grammar for this particular string. If I go for putting parse trees, I will get two different parse trees. It means what? Still this grammar is ambiguous. See here you can see opening, closing, opening, closing, opening, closing. This is opening, closing, opening, closing, opening, closing tree, first tree. This is second tree obtained. Are both the trees different? Yes, the grammar is ambiguous. Then question is, why still the grammar is ambiguous? In spite of eliminating epsilon productions, as I said, it will reduce ambiguity, but it will not go for eliminating ambiguity. Then from this grammar, why, where it is leading to ambiguity? So, you can see the third rule, yes tends to yes, yes. So, this rule leads to ambiguity, leads to alternative paths. So, how to overcome that rule? The second technique, eliminating symmetric recursive rules. So, this rule is symmetrically recursive, both the ways, left recursive and right recursive. So, what to do? So, this rule to be replaced by S tends to S S1, that is forcing it to branch towards the left, and S tends to S1 S, forcing it to branch towards the right. So, previously it was branching both towards the right and towards the left. So, it was leading to ambiguity, whereas now what we are doing, either we can go for forcing it to branch towards the left or forcing it to branch towards the right. So, the grammar obtained now is, previously you had S star tends to epsilon, S star tends to yes, okay, and now what we did, the third rule S tends to SS, this third rule S tends to SS is replaced by one rule, either left or right. So, here we will go for branching it only towards the left. So, we will take S tends to S S1, and now S tends to S1 is the rule to be added, wherein S1 is what? S1 tends to opening parenthesis S closing parenthesis, or S1 tends to opening and closing parenthesis. So, this is the grammar obtained after eliminating epsilon productions and removing symmetric recursive rules and forcing them to branch only towards the left side. So, if you see, this is the unambiguous grammar obtained for the balanced parenthesis after applying elimination of epsilon productions and elimination of symmetric recursive rules. And if you see, this is the only one parse tree obtained from this grammar. No two parse trees can be generated because it is unambiguous grammar. So, why? We will discuss about it later. So, here we discussed about two. One is eliminating epsilon productions, eliminating the symmetric recursive rules. So, this whatever technique we applied for balancing the parenthesis by removing the symmetric recursive rule, we can also apply it on your arithmetic expression. In your arithmetic expression, what we discussed, there are two problems. The grammar is ambiguous because of two ways. It fails to specify associativity. What do you mean by this? For example, there are two parses for the string id plus id plus id corresponding to the bracketing. It may be first and second IDs in parenthesis in bracket, or second and third. So, which is not been specified in your grammar. Next is, it fails to define the precedence hierarchy for the operators plus and multiplication. So, first priority must be given for addition or first priority must be given for multiplication is not specified. So, because here if I take a string id plus id into id, as you have seen, first you can perform id plus id then into id, or first you perform id into id then you go for adding the id. So, because of these two major problems, this grammar is ambiguous. So, how to eliminate? So, on eliminating the ambiguity from the grammar, the unambiguous grammar obtained for this arithmetic expression is this, which is free from ambiguity, and you will get a unique parse tree. How? By applying two things. What were the two problems? First one is for identical operators. So, for identical operators, what we had to do? What we have done is we have forced branching it to go in a single direction, either it may be in the left direction or in the right direction, but right now we have taken left direction. E tends to E plus, T tends to T into. So, we have taken left direction. Then for the second problem, that is precedence hierarchy, what we have done is we have added the levels. So for expression is equals to expression plus term. Term is represented by T, where E expression is term. Term is equals to term into factor, where factor is represented by F, or term is equals to factor, and factor in parenthesis expression, or factor can be ID. And you can see here we have given the precedence first for the identifier, then for the opening and closing parenthesis, then for multiplication, and then for addition. Once we have put the precedence and applied the branching in one single direction, then the grammar obtained will be unambiguous. You can see here a single parse tree is obtained from the unambiguous grammar for the arithmetic expression. So these were the two trees which we had obtained, and you can see here a plus 2 plus 3 into 5, 2 plus 3 into 5. So one had got 17, another had got 25. So at that time, which evaluation must be done first? Now you can see here what we have done. We have given multiplication higher precedence than addition. So at that time, what happens? So first we will perform 3 into 5 multiplication. Once it is been multiplied, then we go for adding it with 2. So this is the right parse tree, whereas this is the wrong parse tree obtained, because first we are performing addition and then multiplication. So from this grammar we get only one parse tree, hence the grammar is unambiguous. Now we have proved that given a grammar is ambiguous. How we have proved? I have a grammar, I take a string, put two derivations, it may be left or right or both left, right, obtain the parse trees. If both the parse trees are different, then the grammar is ambiguous. Then the question, how do you prove that the grammar is unambiguous? For example, a grammar is unambiguous if and only if for all the strings W, at every point in a leftmost derivation or a rightmost derivation of W, only one rule in the grammar can be applied. So it means what? When I go for deriving a string from a grammar, it may be leftmost derivation or it may be rightmost derivation. But at a time, at every given point of time, I must get only one rule to be applied. Then only I can say that the grammar is unambiguous. For example, so we will take the same parenthesis example where we have eliminated all epsilon productions and symmetric productions, and this grammar is ambiguity free. Now, once we go for deriving the string, we obtain this parse tree. So how can I say that this grammar is unambiguous? You can see the rules here. You have three non-terminals, S star, S and S1. Now, first, if the language consists first string as epsilon, at that time which rule will apply? Rule 1. So S star tends to epsilon. If I want to derive a string, not epsilon, then quite obvious it will go for the second option. S star tends to S. So there is no ambiguity. At a point of time, we have only one derivation. If epsilon, we go for choosing one. If not epsilon, then S star will be chosen as S. Next, coming to S1. S1 tends to opening parenthesis, S closing parenthesis. S1 tends to opening and closing parenthesis. We have two rules. Now, if I want to immediately derive a opening and closing parenthesis, then we go for choosing rule 6. If not, then if we go for choosing rule 5. That is, if I want to go for a simple opening and closing parenthesis, apply rule 6. If I want nested parenthesis, a parenthesis within a parenthesis, a parenthesis within a parenthesis, at that time, no choice, we have to go for rule 5. So again, at a given point of time, I have only one option of selecting rule 5 or rule 6. Coming to S. S tends to S, S1 and S tends to S1. So, if you see here S tends to S1 and S1 tends to opening parenthesis. This will work when, if you see here, one opening parenthesis and one closing parenthesis, this is one pair of parenthesis followed by a siblings of opening and closing. At that time, we need by default rule 3. If not, I need only one pair of opening and closing, then I am enough with S tends to S1 by applying rule 4. So, if I do not need siblings of pair of parenthesis, I go for rule 4. If I want continuous siblings of a pair of parenthesis, I go for rule 3. So, at this point of time also, at any given point, I have only one rule matching to derive a particular string. Hence, we prove that the grammar is unambiguous. So, till now we discussed a grammar is ambiguous, how to prove that the grammar is ambiguous, how to prove that the grammar is not ambiguous, and then coming to, can I go for eliminating ambiguity? Then we said we can go for eliminating or reducing ambiguity by applying epsilon productions or by removing symmetric recursions. But there are some more grammar which are by default ambiguous. Such type of grammars are called as inherent grammars. So, let us discuss the definition about what do you mean by inherent ambiguity. In many cases, for an ambiguous grammar, it is possible to construct a new grammar that generates L of G with less or no ambiguity, however, not always. So, this just now we have proved either we can remove ambiguity or we can reduce ambiguity. But some languages have the property that every grammar for them is ambiguous. We call such languages as inherently ambiguous languages. For example, I have a language a raised to I, b raised to j, c raised to k, where I, j, k is greater than or equal to 0 and condition is I is equals to j or j is equals to k. What do you mean by I is equals to j? Number of a's are equal to number of b's, or j is equals to k means number of j's are equal to number of k's. Number of b's are equal to number of c's. So, given every string in L has either or both the same number of a's and b's or the same number of b's and c's, then can I part this language into two languages, wherein one language is L1, a raised to I, b raised to j, c raised to k, where I is equals to j, and the other language L2, where a raised to I, b raised to j, c raised to k, where j is equals to k? Yes. So, the language can be parted into, first I is equals to j, then a raised to n, b raised to n, c raised to m, where n and m are greater than or equal to 0, or means union j is equals to k. J is equals to k is number of b's are equal to number of c's, b raised to m, c raised to m, a raised to n, where n is greater than or equal to 0. Now, if we go for writing the grammar for these languages, if this is L1 and this is L2, and say suppose the start symbol of this language is S1 and the start symbol of this language is S2, then the grammar written will be S1 tends to S1c or A tends to AAB or epsilon. So, these are the rules written in order to generate the first language L1. Similarly, S2 tends to A, S2 or B, B tends to B, B, C or epsilon. So, these are the rules written to generate the second language, that is L2. Now, the language is L is equals to L1 union L2. So, what we will do? We will go for a new start symbol S tends to, start symbol of L1 is S1 or start symbol of S2 L2 is S2. So, S tends to S1 or S2. So, first rule itself you see there it leads to ambiguity. If I go for deriving a string starting with s tends to s1, I get that string. The same string can be derived if I start from s tends to s2. You can see an example here. The example string is a raised to 2, b raised to 2, c raised to 2. It has two distinct derivations, one through s1 and the other to s2. So, you can s tends to s1, other derivation is s tends to s2, obtaining a raised to 2, b raised to 2, c raised to 2 from the same two derivations. When you put the parse trees, you can see here for these two derivations both the parse trees are different. Hence, given any grammar that generates a language, there is at least one string with two derivations in G. By default, this grammar is ambiguous because I have two alternatives at the start of the derivation, S deriving S1 or S deriving S2. Hence, such type of grammars are inherently ambiguous grammar from which we cannot reduce the ambiguity or eliminate the ambiguity. So, both of the following problems are undecidable. Given a context free grammar, is a grammar ambiguous? Given a context free language, is that language inherently ambiguous? For these two questions, we do not have any algorithms as such. Hence, these problems are undecidable problems.